And now we will go to the latent heat of vaporization. This is a continuation only for the theories and concepts of thermodynamics as we go along the way before solving various problems regarding thermodynamics. Okay? So that we can understand. Okay, then we have number 3, the latent heat of vaporization or the heat of vaporization. Okay? So guys, I forgot to tell you that the specific heat capacity from its unit alone, 1 calorie per gram degree Celsius. That means the amount of heat energy in terms of calorie needed, okay, for 1 gram of substance, okay, at degree Celsius. Okay, 1 degree Celsius, something like that. Okay, the amount of heat required, or the amount of heat necessary, like that, to raise the 1 gram of a substance or the water at 1 degree Celsius. You should always take note the form, the unit, and you can create your own definition. Okay, through the unit alone. Okay, of the value or of the specific constant. Okay, like that. Since that is needed man to raise, okay, because that is so that we can attain that specific heat capacity, okay, of course. Okay, so that's the definition of specific heat capacity. So are you all ready now for the fill in the blanks questions or definition type of questions, enumerations, like that? Not only multiple choice, huh? Okay, because multiple choice is very easy to guess, something like that, but the one can measure your ability is problem solving, and fill in the blanks, okay, the enumeration, the listing of the different processes, terminology, something like that, and sometimes the essays, okay, essays question to measure your IQ, intelligence quotient, learning capability, okay, something like that, okay, by your own. Okay, not depending on the books. Okay? Like that. Because if you understand, you can have your own definition. Okay? Number 3. But still a pattern to that original statement. What I mean is not word for word. Okay? It's just the same, but you phrase only what you understand. Not really pattern to the book. But it have the same meaning, something like that. Okay? You can create. Okay. Number 3. Okay, so we recall the value of specific capacity is 4,184 joules per kilogram degree Celsius or 1 calorie per gram degree Celsius. Constants ni siya ha for CP. Not cell phone, but specific heat capacity that we used in the formula Q is equals to mCp/dt. Ganon. Okay, so number 3, latent heat of vaporization. Okay. Some books having the word latent and some books don't have the word latent. So it's merely just the same. Okay? Okay. Or heat of vaporization. In this class, the process, the physical process is evaporation. Okay? Okay, the process evaporation, but the water will undergo vaporization. Meaning to say, the liquid state will change into vapor state. And on. So heat of vaporization. So don't be confused also with the terms evaporation and vaporization is just the same. Okay? So this one. Latent heat of vaporization and evaporation. Okay. In here class, there's no temperature involved in the unit. Okay, it's just easy compared to the specific heat capacity. And again, it has the same purpose with latent heat of fusion. You will multiply this to the different energies, quantities such as the internal energy, change in internal energy, the work, the heat, the enthalpy or the entropy. Okay, entropy, the randomness and disorderliness of the system of the surrounding. Something like that, okay? So if you multiply that there, different types of energies, it will be cancelled the denominator, okay? Because the value of this is 2,160 kilojoules per kilogram. So, okay, kilojoules per kilogram. So if you have the mass of the water, again, because this is water, standard of water, so it will be cancelled, and what is left is the kilojoules, which is the unit of the energy. Okay, like that. So again, if the problem having this as a given, then bingo, you can solve for the internal energy, the work, the enthalpy, like that, without any temperatures changes. Because this is dependent on the temperature, something like that. But this can be attained, this value, at 100 degrees Celsius, or boiling point of water during evaporation. So, you will ask also to me, sir, what is the meaning of boiling point? You have to know that the boiling point has also its own definition, so that you can understand also that this is going to be, the boiling point is 100 degrees Celsius, that is necessary to obtain this value of latent heat of vaporization, or the heat of vaporization. Because without this boiling point of water, there will be no value of this latent heat vaporization and heat of vaporization value, which is 2,260 kilojoules per kilogram. So that is the basis now. Okay, boiling point is the vapor pressure of the water will equal to the surrounding liquid. The liquid itself, the surrounding liquid, right? We put that in the kettle, not the vapor, because I said the vapor pressure, meaning the pressure of the vapor that will escape to the atmosphere, right? So the vapor pressure will be equal to the pressure of the surrounding liquid. So the liquid surrounding inside the kettle. So if we attain that one through 100 degrees Celsius, that is the boiling point of water, and that is the basis to obtain this value of latent heat of vaporization. Okay, memorize. Okay, this one, and then memorize also the molar latent heat of vaporization value, which is equal to, okay, 40.8 kilojoules per mole. Okay. Which is which? You can use this one depending on the problem, because the problem only will give the chemical reactions again. For example, nitrogen gas, ganun. Okay, plus hydrogen gas to produce ammonia. Example only. And you're given the latent heat of vaporization of ammonia. Okay, like that. So there's no mass given the problem. So use the number of moles in a chemical reaction. Since this is 4.08 kilojoules per mole times the number of moles in the chemical reaction that you're requiring to, then bingo, you can solve for the enthalpy, entropy, work, and internal energy. Even though there's no temperatures involved, there's no volume involved, there's no pressure involved, like that, there's no thermodynamic processes involved also, which is the isocaloric, isovolumetric, isothermal, adiabatic, isobaric, right? The different processes of thermodynamics, you have to understand that also. And its equivalent formulas that I discussed yesterday. Okay. That is the latent heat of vaporization and heat of vaporization. Okay. Now, class. So we need to know the definition of latent heat vaporization or heat of vaporization. So what is the definition now? Okay. It's very clear in the unit. Okay. The amount of heat energy, because it's referring to heat again, that's heat energy automatically. Okay, is the amount of heat energy required or needed, okay, to change the 1 gram or the 1 kilogram, because kilogram is the denominator. Be careful also, if the denominator is gram, your definition also in gram. Okay, if the kilogram is the denominator, your definition also in kilogram. Okay. Okay, so the amount of heat energy required or needed in terms of kilojoules needed for 1 kilogram of a substance, okay, liquid to change into vapor state. because it's changed from liquid to vapor. Okay? Or liquid to gas. When you mean of gas, that's already vapor. Okay? Gas exists through vapor state manggod siya. So it's just the same. Liquid, a change from liquid to vapor or a change from liquid to gas. Because gas automatically a vapor. Okay? So don't be confused with the vapor and the gas also. Maybe you will confuse also. Oh, I love to use gas. It's just the same. Okay? So that's the definition. By the unit alone, you can create your own definition. Okay? Because sometimes in the, examination, there is like this through statement naman good siya. So, blank is the amount of heat energy that is necessary, okay, needed for a 1 gram of a liquid or 1 kilogram of a liquid to change into its vapor state. So the answer will be latent to the heat of vaporization, because the choice is also A, latent heat of fusion, B, latent heat of condensation, ganun siya, C, specific heat capacity, D, latent heat of vaporization. So your answer will be latent heat of vaporization. Okay? Your identification is independent with temperature. Okay, in the denominator. But at 100 degrees Celsius, this value can be attained or obtained. Okay? That is latent heat of vaporization and heat of vaporization. Any questions so far? Okay. For example, if we have formula in the first law of thermodynamics, as you can remember, we have heat Q. Okay. Q can be changed also with the term enthalpy in the problem. Okay. Like if, for example, what is the enthalpy of the system? That's also heat. Ay mo kalibo kay enthalpy heat ra gyud na siya pod. Okay, but this enthalpy is just only the total of the heat in the system. Okay? So, ganun lang siya. Terminologies. Okay, Q is equals to delta U, or internal change in internal energy plus the work. This is from first law of thermodynamics. Okay? Like this. Okay? First law of thermodynamics, which is the law of conservation and energy that states energy can neither be created nor can be destroyed, but it can only be transformed to various types of energies, such like this: internal energy, work, heat energy, and the rest of the energies that I mentioned yesterday. A lot, right? We have the pneumatic energy, hydraulic energy, geothermal energy, okay? Power energy, something like acoustic or sound energy, light energy, chemical energy, mechanical energy, electrical energy, thermal energy, radiation energy, blah blah blah, chuba chuchu. Okay? There are at least 15 types of energies, plus the potential energy and the kinetic energy. There's a lot of energies. All that energies, study very well, understand what is that all about, and then memorize the K terms for that, because it will come up in the examination, 100% sure. Okay, like that. Especially in in physical and chemical principles. Okay, like that. So Q is equals to delta U plus work. And now, okay. So if we have this kilojoules per kilogram, and then we are given the mass, then we can add that here also. Okay, for example, the internal energy of the system is ganon, 2,200 kilojoules, and the water flow in that particular system, the water flow in that particular system. Okay, like that. What is the total work in the system? Ganun na siya ka-simple, usaray given. Okay? One given only, but you can compute already. Okay? So, what is the work done by the system? Ganun siya. Oh my gosh, only mass is the given and I could ask by the work alone. Okay? So, that's the magic for theory and concepts. Okay, because normally you will be panicked because there's only one given. So normally kasi in mathematics, in equations and formulas, there must be at least 2 or 3 to solve. Okay, but in here, even though only one given in the problem, you can solve because you have the theory. okay, that the latent heat of vaporization of water, like that at 100 degrees Celsius, is equal to 2,260 kilojoules per kilogram. Then multiply the mass, I can get the heat energy, and that is for the work. Ganun siya. Okay? And then because you can compute that one through this equation. Ganun lang siya. Simple ra kayo siya. Okay? And then, if the problem also will state the chemical reaction again, we have also the standard value of 40.8 kilojoules per mole for the water, for the latent vaporization. So automatically you can set also the work, the energy, the Q, even though only one given. Or even though there's no given at all. Because the chemical reaction is not really given, it's only a chemical reaction. For example, water, okay, the water produce a chemical reaction of example only, 2H2 plus 2 moles of oxygen goes to water. What is the work done in the system? As simple as that, there's no given at all. How can you compute that one? Because we have latent heat of vaporization equals to 40.8 kilojoules per mole, then times the number of moles in the stoichiometric relationship in the chemical balance reaction. So you can cancel the moles, and what will remain is the kilojoules, is the heat energy, or it could be a work, it could be an internal energy, then bingo, you can solve even though there's no numerical figure given in your problem. Like that. Sometimes it's gonna be like that, okay? So, sometimes we will be panicked because that's time pressure kasi, okay? And oh my gosh, what's this? But actually, it's very easy to compute also. And then we will try, it's very difficult, but it's not very difficult. It's not difficult, really, only theory and concepts will matter. Okay? Like that. Okay? So, that's the technique, ha? Basta na-adjust gani siya latent heat of vaporization, latent heat of fusion, then bingo. You can solve for energies. Then, if there are masses given, then multiply the value of this latent heat of vaporization on the latent heat of the fusion. Then you can substitute that in the first law of thermodynamics equation. Then bingo, you can solve. Okay, because there's a lot of quantities also: temperature, pressure, volume. So you are dependent to that, especially in the ideal gas law. Okay, in fact, there is also R, universal gas constant. Okay, the capital R. Okay, which is, I think, based on my stock knowledge, that is, oh my gosh, I forgot. No, wait, 0.08205 liter atmosphere mole over mole Kelvin. That's in terms of liter atmosphere. But in terms of joules, I think so. I think, but not really sure because it's only stuck in my brain cells. It's 8.314, something like that. 8.413, something like that. 8.416 or 8.415, something like that. Joules per mole Kelvin. Okay? Hindi na siya liter atmosphere. Okay? Wala na siya atmosphere. Kaya energy naman siya daan sa numerator. Okay? Like that. So, that is in terms of joules per mole Kelvin. So it's up to you. We'll use that in the equation of the ideal gas constant. That's too much heat A. In here, in latent chuba chuchu, there's no universal gas constant needed, there's no pressure needed, there's no volume needed, there's no temperature needed to solve the problem. So, no headache. Okay. Right? Okay, that's number 3. Latent heat of vaporization and heat of vaporization. Okay, guys, if you understand what I'm talking to in the discussion, then you can comment in the comment section down below, and you can also subscribe to my channel if you aren't subscribing yet, and you can click the notification bell of some news updates. So we'll see your eternal voice. Bye bye, everybody. God bless. See you later.